Hello everyone and welcome back to the Academia and Research Collective. My name is Darren and today I wanted to make a follow-up video to my last video where I talked about my experience at the UF SSTP summer camp. But this time I wanted to specifically focus on my research project there. You see, I want to dive deep into my research project today, but also talk about how I worked in a lab and also concurrently worked on my research project at the exact same time. But I also want to present my research today in the same manner that I would present it at a science fair competition, so that you can get a feel for what it's like and how you should be presenting along a similar lines at things like science fair, JSHS, or Invention Convention, all those different competitions. So hopefully by the end of this video, you'll be able to understand my project, have a rough understanding of how you should be presenting, but also see how you can actually apply the things we learned in our Introduction to Research series in research and in your presentations. So without further ado, let's get straight into it. My project at UF was 3D VoNerf, 3D diffusion-based voxel optimization for volumetric denoising in neural radiance fields. It's quite a mouthful, but I promise I'll break everything down. Firstly though, I usually don't talk about this in a presentation, but I wanted to reiterate again that I worked in the Florida Optics and Computational Sensor Lab, or the Focus Lab, while at UF. I had a wonderful time there. Now, before I actually talk about the bulk of my project, I wanted to talk about some precursors. The first thing you need to know is what a neural radiance field is, or a NERF. A neural radiance field is a type of AI model. I think it came out around 2020. What it does is that it's able to turn 2D images into 3D representations. And how it works, you can see in the diagram on the screen, is that the AI model shoots like rays through the pixels of 2D images. And where those rays intersect, it can actually predict what it's supposed to look like in 3D space. So it's super cool. Now, if you have a hard time visualizing that, you can refer to this here. Each of those red squares is a 2D image in what it sees. You can see some images on the right-hand side of the angles of this garbage can. But what we're trying to do is to basically predict those gaps in those red squares, because that's incomplete, but if we had all of those different images, we have a full 3D model. And so this is what we're trying to do with NERF, and what my project is trying to do as well. However, neural radiance fields have a big issue, and that's the issue of noise, or random pixels, or blurriness. You can see on the screen here, this is supposed to be a 3D scene of a tank, but the tank looks really bad. I don't even need the red squares to highlight where it looks bad, but you can see all those blurry and fuzzy areas. That's really bad. We want a clean 3D scene, and that is the heart of my problem. This goes back to what we learned in Introduction to Research series, where you have to identify a specific problem. My specific problem this time is the issue of noisy representations in neural radiance fields. So I have my problem. That's a check. Now, here's my research question. And how I formulated this research question, though, was after reading a lot of literature on neural radiance fields and denoising. And so my research question and my guiding question, remember we talked about that in our Introduction to Research series, is how can we use neural radiance fields to generate accurate 3D representations that have minimal degradation and noise? What I'm trying to do is to get the image on the left that's super blurry and to change it to the scene on the right, which is much more clear. And so this is the question that I'm going to be trying to solve throughout my research. It's so important to have a research question to make sure that you're staying on track throughout your research. And so my goal, once again, sometimes you have hypotheses or you have engineering goals. This time I'm choosing goals. And so what I wanted to do was to enable continuous denoising throughout the training loop of a NERF to minimize artifacts or noisy areas through 1, using 3D diffusion, and 2, using density attenuation. I'll go into both of those in a second. But you can see here, you should specify what your goals are, right? It's the same thing with your research question, like we learned in the Intro to Research series. This is how you stay focused on your project to make sure you aren't wandering off in some random direction, that you're actually trying to solve what you set out to solve. Now, 3D diffusion. What is it? Well, 3D diffusion is basically another type of AI model that can basically turn random 3D pixels into an object. And so this is a diagram I mocked up. I worked at UF, so of course I'm going to try to make a gator. But as you can see, we first start on the left-hand side with a lot of random noise. This noise means nothing. And through each step, the AI model is able to turn it into something. So the second step, it looks like some kind of longer blob. By the third step, it's going to take the shape of a gator. And by the fourth step, you can tell that that's a gator. And so this is how a 3D diffusion model produces stuff. But how does a 3D diffusion model train? Well, how it trains is that it actually starts off with the clean image. So we give it the clean gator, and it learns to add noise through each step to learn what the image looks like with more noise. But all you need to take away here is that a diffusion model generates by removing noise, and it trains itself by adding noise. And so that's what 3D diffusion is. You can see as I'm explaining this, like I would at a science fair competition, I'm explaining all the necessary components. I'm saying just enough so that a person with no knowledge can understand exactly what I'm talking about, but also not bombarding them with information. And so now that I have some of these prerequisites, here is our main theory. One of the main theories that I have is something known as if we pass a random noise through a diffusion model. You see, I want to denoise neural radiance fields. So my theory is that if we pass something noisy, some noisy sample of pixels through a diffusion model one time, we should just get a lot of random noise, right? Random noise is just random numbers. If we pass some random junk through a diffusion model, what we should get on the other side, if we pass it one time, should just be more random junk. And so there's a huge difference between both of the noise samples that have not gone before or have already gone into the diffusion model. Contrast this with the last slide. If I pass in the clean gator into my 3D diffusion model, it shouldn't change it that much. It should already understand that it's a clean gator. We don't want to change it that much. But if I pass in something super noisy, it'll try to change it a lot. And so the image that we take from beforehand and afterwards to the diffusion model should look significantly different. Now remember that, because that's going to come into play later on. Now here is my entire pipeline. This is the whole representation and the whole architecture of what I'm trying to do with my project. And so let's break this down into easier chunks to understand. And this is also what you should be doing when you talk to judges. You don't want to throw them this huge diagram and then just go, so here's our diagram. That's going to confuse them. So what you want to do is break it up into chunks. So let's go to the first chunk. This is sparse voxel rasterization. This is just a fancy name for the neural radiance field we chose. It's a type of NeRF model, and how it works is that we take 2D images and we voxelize them. What does voxelize mean? Basically, we turn them into little cubes of information, and each of the corners of those cubes stores vital information. This information we call the density field. It basically controls how transparent or how opaque that one pixel is. Okay, so that's all you need to know, is that it starts with 2D images, it voxelizes them, turns them into cubes, and then it creates a density field out of all of those corners of those cubes and trains itself to basically turn those density fields into a proper item. And so this on its own would be what NeRF is, right? It's just using those density fields to create a 3D generation. But instead of continuously looping the density field back to the training images, what we do is that we hack it and we pass it along to our 3D diffusion model. And so what we do is that we grab the density field from the neural radiance field and we pass it into our diffusion model. And our diffusion model does something really special. It does something known as density binarization. And so what we're doing in this case is that we're looking at the pixels of a 3D scene. And if those pixels are above a certain level, if they're super transparent, then we cut them away. We don't want them, because mostly things that are super transparent are going to be those fuzzy areas. Like remember when you saw in the tank, is those super fuzzy areas. But pixels that are really solid, if I have an apple and it's super red and super solid, then I want to keep it that. And so what I'm binarizing is, I'm binarizing between transparency or solid. And then we update the density field to reflect how solid or transparent it is, and then we keep training to remove those areas of noise. Now, we also do something known as density attenuation. Density attenuation is another part of my project where we basically are comparing the original density field and the enhanced density field. Remember we talked about earlier, if we pass noise through a diffusion model one time, if it's a noise, it should continue to be noise, but if it's clear, it should not really affect it that much. And so the enhanced density field is the density field we've passed through the diffusion model, but the original density field is a density field that was never passed through. Now, very clear images, if we compare them, or subtract them in this case, that's the same thing. If we compare a clear image that we've passed through a diffusion model, there shouldn't be that much of a difference. But if we send through noise, the enhanced and original should look a lot different. And so what we're doing in density attenuation is we're saying, okay, this area, if I pass it through the diffusion, looks a lot different. This probably means it's noise, so we want to kind of make it less transparent and less transparent. But this area, it's really solid. It looks really good. If I pass it through a diffusion model, it still looks the same. We keep that the same. But if it's noisy, we make it more transparent, and eventually it should completely disappear. And that's basically the premise and heart of this project. Now, this is a long formula, density to alpha. Alpha is what really controls if an image becomes solid or an image becomes fully transparent. You don't need to know the inner workings of this. All you need to know is that density is directly related to alpha. So lower density value means that the image is more transparent, or higher density value means that it is more solid. And so if we minimize the density, we'll also make it more transparent, which is what we're doing with the noisy areas. And so now, after getting through the heart and methodology of my project, I'm going to talk about my data set. So I use two different data sets to test my project, and that's Nerf Busters as well as the DL3D V10K data set. Both of these are just super diverse data sets of a lot and a ton of images in them. But you see, as I'm walking through this process, as I'm presenting all of the different steps of my methodology, from how it works to how I'm testing. And right now I'm talking about how I'm testing with my data set. Those are all things that you should do as well. And so here are some of my qualitative results. After I talked about how I made my thing, how I'm going to test it, now I'm going to show you the results. So on the left-hand side, you have the ground truth, which is what the image should look like at that area. GANNERF and NERFLIX in the middle are two of the current models, and I'm comparing those to 3Devo Nerf. Qualitatively, you can see that 3Devo Nerf is a lot better quality than GANNERF and NERFLIX, which is good because we're beating what's currently out there. So here are some qualitative results. Now here are some quantitative results. So when you present quantitative results, you want to explain to your judges what they're seeing, right? They probably don't know what PSNR, SSIM, or LPIPs are. And so in this case, I would explain to them. PSNR, SSIM, and LPIPs are three metrics of image quality that we use in computer vision. PSNR, SSIM look at the pixels more, but LPIPs uses a special method to compare if a human were to look at two images, how similar would it compare it? PSNR, SSIM should be as high as possible, and LPIPs should be as low as possible. So as you can see here, 3Devo Nerf beats out all of the current methods in terms of PSNR, SSIM, and LPIPs. And I've even bolded all of the numbers in the 3Devo Nerf category to show you that my quantitative results tell that we have made significant results. And so whenever you're explaining results to your judges, you should try to use both qualitative, if you have qualitative, as well as quantitative data. But you also explain the metrics. Don't assume that they immediately know what the metrics are. Even if it's a quick 10 to 15 second explanation, it is worth it. Because you also want to show your judges that you know what you're talking about. And then finally, I like to talk about my future work. So what I want to talk about here is that I wanted to accelerate my training times. I wanted to implement smarter voxel and density pruning. So how we get rid of voxels or how we remove those transparent or fuzzy areas. And then I also wanted to adapt my things to other fields, such as robotics, autonomous vehicles, or medical visualizations. Every single project, I highly recommend at this end of your presentation, you talk about what you're going to do in the future. Judges love hearing about how you want to continue your project or how it can be applied to other areas. If you're just doing research and then you stop it after you present at a science fair, they don't like that. And usually there's a category on the rubric that talks about how continuing. And if you talk about continuing, you'll get more points there. So I always highly recommend you end off your presentation when talking about your future work. And then I have a key citation section. I always talk about it like, here are some key citations, spend like 5 to 10 seconds on that. And then lastly, I always ask any questions. And so from here, there's a question back and forth session, which is really useful. You want to answer those as confidently as possible. And of course, as always, you've probably heard this before though. If you don't know an answer to a question, don't lie. Just say things like, wow, that's pretty interesting. Maybe it's something I can look at in the future. Don't lie, because then if you get caught in a lie, that's even worse. And so yeah, so that is my project in a nutshell. Now usually I would stop and end my presentation here and just let them ask questions, but today I also wanted to show you what my project led up into, which was I ended up writing a paper on it. As you can see on screen here, it's my paper. It includes all the diagrams that I showed you today, but it just runs through basically this presentation I'm giving you right now in a paper format. And then here's my poster. If you look at the poster closely, every single thing I mentioned to you in the presentation is a part of my poster. The issue of NERF in the top left, what we're doing, our research question, our goals, explaining 3D diffusion, what it is to give you background information. I give you the entire methodology and our proposed framework. And then if I'm presenting to judges, I'll point to my poster and break down every single step. And then I have my qualitative, quantitative results and my future work. So everything I told you today should be on your poster board. And you should be referencing your poster board as you're talking as well. And so this is an example of a poster board that I made while I was at my research program. And this is something you should be doing similar. Now you don't have to, and this is a disclaimer I want to say, is that you don't have to present in exactly my format or style, and you don't have to make a poster or paper like my style. But what you should be doing is to hit on all of those things that we talked about in the Introduction to Research series, because it shows a story, right? Judges love when you tell them a story. Here's where I started, here's what worked, here's what didn't work, here's what I'm going to do, here's what I did, here's how I tested it, and here are my results, and here's what I'm going to do in the future. It's a linear progression of things that you're doing, and that's always great for understanding for your other judges as well. And so finally, I wanted to talk about was, quickly the experience of working in a lab like this while working on this project. Working in a computer science lab is probably different than things like wet labs where your professor is always working with you and it's super, super hands-on. For a computer science lab like myself, I was working with my PhD students. I would code alongside them and research and read papers all day. If I had questions, I would ask them and they would help me troubleshoot some code or just something not working with my VS Code or GitHub, and they would help me there. And so that's what it was like working in a computer science lab. But if you're working in a wet lab, that's probably a whole different experience. Now, I don't have much experience working in a wet lab. Actually, I have zero experience working in a wet lab because that's not where my area of focus is. But I assume it would be something similar to where you have your professors and your graduate students helping you along guidedly. But from a computer science perspective, it's kind of sitting behind a computer at a desk all day. You ask your graduate students or your mentors questions. If you have something that comes up along the coding process, they help you troubleshoot some stuff, come up with a lot of methodology and tests. That's a big thing about computer science is we might not know how something is exactly going to work, so we're going to run a bunch of tests on them, and coming up with those tests is super, super important. And that's what I leaned on my professors and my graduate students for. And so that was a super useful part of working in the lab because I got to instantly ask them questions as opposed to independent research where you might have to search online for hours. So this was a really, really, definitely a transformative experience. And I once again highly recommend that if you're a rising senior to apply to the UF SSTP program. So yeah, I hope that today you got a lot of understanding as to my project, but most importantly, you understood how you can present in a style that's similar to science fairs and how you should be doing it at science fairs. Of course, you don't have to copy my style exactly. I'm just trying to give you a framework. And lastly, also what it's like to work in a lab or also work on a computer science project. I hope that this was informative for you, and thank you for watching the Academia and Research Collective. I'll see you next time.